Welcome to Understand the Math. In this Calculus 1 video, we're focusing on how to calculate limits using limit laws. You'll see how the basic limit laws work, how to evaluate limits that lead to indeterminate forms, and how the squeeze theorem helps in difficult cases. I'll walk you through lots of examples so you can see how this works in practice. Be sure to download the free guided notes to help you follow along step by step. We're going to start with learning the limit laws and then walk through some algebraic and graphical examples. For the limit laws that we're going to look at, we're going to assume that the limit of f of x as x approaches a and the limit of g of x as x approaches a exist, and c is a constant. The first limit law that we're going to look at is called the sum law. It tells us that the limit of a sum is just the sum of the limits. The second one is the difference law. And just like the sum law, it tells us that the limit of a difference is the difference of the limits. Let's now look at our third law. It's called the constant multiple law, and it tells us that the limit of a constant times a function is just the constant times the limit. That just means that you can bring the constant out in front of the limit. Our fourth law is called the product law, and it tells us that the limit of a product is just the product of the limits. Our fifth law is really similar to our fourth law, and it's called the quotient law, and it tells us that the limit of a quotient is just the quotient of the limits. We have two laws left, and they're related. Law number 6 is called the power law. It just tells us that the limit of a function raised to a power is the limit of the function all raised to that power. Our last law, number 7, is the root law. It tells us that the limit of the nth root of a function is equal to the nth root of the limit of the function. That just means you can pull the limit inside the radical. We're going to be looking at some examples next, and for some of these examples, we're going to need to remember that a limit does not exist when the left-hand limit does not equal the right-hand limit. We're going to look at some examples where we're going to use limit laws to evaluate some limits. We're going to start with some algebraic examples. We're given that the limit of g of x as x approaches some number a is equal to 0. The limit of h of x as x approaches a is equal to 9, and then the limit of f of x as x approaches a is equal to minus 5. And we're asked to evaluate the following limits. Let's look at our first one. We want to find the limit of f of x plus h of x as x approaches a, and we're going to use the sum law to evaluate this. The sum law tells us that we can just pull the limit inside and apply it to each function separately. So this is equal to the limit as x approaches a of f of x, which is minus 5, plus the limit as x approaches a of h of x, which is 9, and we get a value of 4. Let's look at example 2. We're going to use the power law for this example. We're going to evaluate the limit of f of x squared as x approaches a. This just means we can pull the limit inside, and we're going to take the limit of f of x, which is minus 5, and then we're going to square that, and we end up with 25. Let's go to example 3. We're going to use the root law to evaluate this one. We're going to pull the limit inside the radical. So we have the limit as x approaches a of h of x, which is 9, and we're going to take the cube root of that. The best way to write this answer is just to write it as 9 to the 1/3. Or you could also just leave it as the cube root of 9. Let's go to number 4. For this limit, we're going to use the product law. So we're going to take the limit of h of x as x approaches a, which is 9, and multiply it by the limit of f of x as x approaches a, which is -5, and we get an answer of -45. I hope that you're getting the hang of this. Let's look at number 5. For this one, we are going to use the quotient law, and we're going to have the limit of g of x as x approaches a in the numerator, and that's going to be 0. And then in the denominator, we have the limit of f of x, and that's -5, so we get an answer of 0. Let's now look at the last one. For this one, we are also going to use the quotient law, and it's just like number 5, except we're just going to switch the numerator and the denominator. So this one is -5 over 0. When we have division by 0, we have an answer that does not exist. So we're going to write our limit as dne. That's just the abbreviation that you use for does not exist. Let's now look at some graphical examples. I think these are a little bit harder than the algebraic ones. We are given the graphs of f of x and g of x, and we're asked to evaluate the following limits. Let's move this up so we can see our limits. And let's start with number 1. For number 1, we're going to use the sum law. So we're going to take the limit of f of x as x goes to 2, and we're going to add to that the limit of g of x as x goes to 2. Now we have to look up at our graph. We're going to be focusing on 2 in both of our graphs. For our first limit, we're going to look at the limit as x approaches 2 from the left and from the right. So it's going to be approaching this number, and that's going to equal 2. So this is going to be 2. Now let's do the same thing for our graph on the right. We are going to be approaching 2 from the left and from the right. And you can see that we get to the value of 0. So we're going to add 0 to this, and then our answer is equal to 2. Let's now look at our second one. Just to save time, I'm going to not write down that intermediate step that we wrote down for the first one. We can just do that in our head. On the graph on the left, we are going to be looking at the limit of f of x as x approaches 1 from the left and from the right. And we can see that that goes to a value of 1. So let's write down 1. Now let's look at the graph on the right. We are going to be focusing on 1. So we're going to look at what happens as we approach 1 from the left and from the right. And you can see that it's not the same value. When we approach from the left, we get 2. And when we approach from the right, we get 1. Those are not equal. So we have to write down that this limit does not exist. And then 1 plus dne is also equal to dne. So that limit does not exist. Let's look at number 3. We are going to be focusing for this one on 0. Let's put a pink dot at 0 so we can know where we're looking. For the function on the left, we are going to be approaching 0 from the left and the right, and that's going to equal 0. And then for g of x, we're also going to be approaching from the left and the right. Here's the left, there's the right, and we're going to get 1. So we have 0 times 1, which is 0. So our limit is equal to 0. Let's look at our last one. For this one, we are going to be looking at the point x is equal to -1. So let's highlight that. For f of x, we are going to be approaching from the left and from the right, and we get a value of -1. So this is -1, and we're going to divide that by our g of x limit. Again, we're focusing on -1. We're going to come from the left and the right up here at g of x, and we get a value of 0. So we have -1 over 0. Whenever we divide by 0, we end up with a limit that does not exist. So we're going to write down dne for our answer. Sometimes when we evaluate limits, we get an expression that doesn't immediately tell us what the value of the limit is. This expression is called an indeterminate form. Let's now learn how to evaluate limits with these forms. Limits of the form 0 divided by 0 or infinity minus infinity are called indeterminate forms. These indeterminate forms can equal 0, plus or minus infinity, or they can equal a finite number. Let's look at an example of a limit with an indeterminate form so that we can better understand this. We're going to evaluate the limit as x approaches 2 of x squared plus x minus 6, all divided by x minus 2. The first thing that you want to do when you evaluate limits is do direct substitution and just plug in the value. This gives us 2 squared plus 2 minus 6, all divided by 2 minus 2. Up top, we have a 4 minus 4, and in the denominator, we have a 0. So this gives us 0 divided by 0. And that's what we call an indeterminate form. To find out what this limit equals, we can look at its graph. The blue line is the graph of x squared plus x minus 6, all divided by x minus 2. To evaluate the limit of this function at x is equal to 2, we look at our graph and look at the limit from the left and the limit from the right, and we can see that that limit is going to equal 5. So we can say that the limit as x goes to 2, x squared plus x minus 6, all divided by x minus 2 is equal to 5. And that's our answer. Notice that there is an open circle at x is equal to 2 because the function is not defined there. It was really nice to see the graph of this function to understand what an indeterminate form looks like graphically. But in practice, it's really nice to be able to evaluate this type of limit algebraically. Let's go ahead and let's do that. We have the limit as x goes to 2 of x squared plus x minus 6, all divided by x minus 2. Notice that our numerator is a quadratic, and we can factor that. So we're going to write this as the limit as x goes to 2. Factoring the top, we can have an x plus 3 and an x minus 2. And we all divide that by x minus 2. You can see that these two terms cancel, and this gives us the limit as x goes to 2 of x plus 3. And now we can just plug in what x is, and we get 2 plus 3 is equal to 5. And that agrees with the answer that we got from looking at the graph. In this last example, we use the algebraic technique of factoring to evaluate the limit. There are other algebraic techniques that we can also use, and we're going to look at those. An indeterminate form, such as 0 divided by 0 or infinity minus infinity, can be evaluated using one of these 5 techniques. The first one is factoring, and then we have multiplying by a conjugate, getting a common denominator, multiplying out a polynomial, or applying a piecewise function definition of an absolute value function. We're going to do an example of all 5 of these. We're going to look at 5 limit examples. And each of these uses a different algebraic technique to evaluate it. Let's look at our first example. The first thing that we always want to do is to just plug in our number and see what we get. So this is 25 minus 5 from the right squared, which is 25, all divided by 5 to the right squared again, so that's 25, minus 10 times 5, which is 50, plus 25. So you can see that this gives us 0 divided by 0, which is an indeterminate form. When we look at this problem, we see that we have a quadratic in the numerator and in the denominator, so that clues us in that we can probably use factoring to evaluate this limit. We will factor the top and then factor the bottom. So we have the limit as x goes to 5 from the right. Factoring the top, we get a 5 minus x and a 5 plus x. Now we can factor the denominator. This is going to be x minus 5 times x minus 5. Let's focus on this term and this term. Those terms are almost the same, they are just different by a negative. So what we can do is we can rewrite the term on the top and take a negative out. Let's write this as the limit as x approaches 5 from the right of minus x minus 5, and then we have a 5 plus x, and then our denominator is the same, x minus 5 and x minus 5. Now let's focus again on these two terms. They are the same now, so we can cancel them out, and we can now go ahead and substitute in that x is going to 5 from the right. This gives us a minus 5 plus 5 from the right, all divided by 5 from the right minus 5. On the top, we have a minus 10, and then in the denominator, we can think of 5 from the right as 5.000, lots of zeros and then a 1, minus 5. So this is a number close to 0, but it's going to be positive. So we have a negative number divided by a really small number that's positive, and that's going to give us an answer of minus infinity. So our limit is equal to minus infinity. Let's now look at our second example. We're going to begin by substituting in that h is equal to 0. This gives us the square root of 1 minus 1, all divided by 0. So we get 0 divided by 0, which we saw up above is an indeterminate form. Often, when we have a limit with a square root, we can evaluate it by multiplying by a conjugate. Let me remind you what a conjugate is. The conjugate of the square root of x minus a is equal to the square root of x plus a. When we multiply it by a conjugate, often terms will cancel out. So that's why we're going to do this. We're going to take the limit as h goes to 0 of the square root of 1 plus h minus 1, all divided by h, and we're going to multiply it by the conjugate. The conjugate is going to be the square root of 1 plus h plus 1. All we're doing is changing this sign. And then we can't change the problem, so whatever we multiply on the top, we have to multiply on the bottom because we can really just be multiplying by 1. Otherwise, we would change the problem. Now let's go ahead and multiply this out. This is the limit as h goes to 0. Let's use the FOIL method and multiply the first terms. So that's root 1 plus h times root 1 plus h. So that gives us a 1 plus h. Now let's multiply the outer terms. So we're multiplying square root of 1 plus h plus 1. So that gives us square root of 1 plus h. Now we're going to multiply the inner terms, and that gives us a minus square root of 1 plus h. And then lastly, we'll multiply the last terms, and that's going to give us a minus 1. And our denominator looks like h times the square root 1 plus h plus 1. Notice that I did not multiply out the denominator. It's always good to hold off not multiplying out the term that doesn't have the two conjugates in it. Now let's see what cancels. This term is going to cancel with this term, and our 1 is going to cancel with our 1. So we have the limit as h goes to 0 of just h on top, and then we have an h in the denominator and a square root of 1 plus h plus 1. Now you can see that our h's cancel, and that's why I didn't multiply things out. And we can now just go ahead and plug in h as 0. We have a 1 on the top. That comes from our h canceling. And then we have the square root of 1 plus 0 plus 1. So this just gives us an answer of 1 divided by 2. And that's what our limit is equal to. Let's now look at our third example. We'll start by substituting in what x is. This gives us 1 all divided by 0 times the square root of 1 minus 1 over 0. This gives us 1 over 0 minus 1 over 0, and that's infinity minus infinity. And just like 0 divided by 0, this is also in indeterminate form. When you have a limit that equals infinity minus infinity, it comes from having two terms, and we can often evaluate a limit like that by combining the two terms and getting a common denominator. So let's go ahead and let's do that. We're going to get a common denominator equal to x times the square root of 1 plus x. We have the limit as x goes to 0. Let's write our denominator first. We have x square root 1 plus x. On the left, we have a 1. And for our term on the right, we only have an x. So we need a square root of 1 plus x. So we're going to subtract square root 1 plus x. Now let's go ahead and plug in x is equal to 0. So we have 1 minus the square root of 1 on the top, and we have 0 times the square root of 1 on the bottom, and that gives us 0 divided by 0, which is our indeterminate form that we looked at for our first and second examples. Notice now that we have a term in the top that's a number minus a square root. That means that we can multiply by a conjugate. Let's go ahead and let's do that. This is the limit as x goes to 0, 1 minus the square root of 1 plus x, all divided by x square root of 1 plus x, and let's multiply by the conjugate, 1 plus square root of 1 plus x, all divided by 1 plus square root of 1 plus x. If I were teaching this in class right now, I would start to get a lot of moans. I know this is a long problem, but hang with me. You can do this. Let's multiply out our top. We'll use the FOIL method. We'll multiply the first, which is 1. We'll multiply the outer terms, which gives us a plus square root 1 plus x. We'll multiply the inner terms, which is minus square root of 1 plus x. And then the last terms, which gives us a minus, and then the square roots combine to be a 1 plus x. And then our denominator, we just have to copy down x square root 1 plus x. Do not multiply the denominator out because we're hoping that terms are going to cancel. Let's look back up at our numerator and we'll cross out the terms that cancel. We have this term and this term cancel, and then our 1's cancel. So let's go ahead and rewrite this as the limit as x goes to 0, we have a minus x up top. And then down below, we have an x, square root of 1 plus x, 1 plus square root 1 plus x. Our x's cancel, which is why we did not multiply out the denominator. And now we can go ahead and plug in x is 0. So up top, we get a minus 1. And then in our denominator, we have square root of 1. And then we have a 1 plus square root of 1. So this is minus 1, all divided by 2. And that's the value of our limit. Remember that in this example, we used two techniques. We got a common denominator, and then we multiplied by a conjugate. Let's look at our fourth example. This one isn't as bad as our third one. Let's start by plugging in h is equal to 0. This gives us a 2 plus 0 cubed minus 8, all divided by 0. So this is 8 minus 8 over 0, which is 0 over 0, which is an indeterminate form. Notice in this problem that we have 2 plus h raised to the third power. Whenever you have a limit with an expression raised to a power, you can often evaluate it by multiplying out that power and then hoping that some terms cancel. We're going to begin by multiplying out 2 plus h cubed. You may not remember that formula, so let me go ahead and let's write it down. A plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. If you don't want to remember that formula, you can just multiply 2 plus h cubed out by hand. I'm going to use the formula, so I'm going to write down this is the limit as h goes to 0, 2 cubed plus 3 times 2 squared times h plus 3 times 2 times h squared plus h cubed. And then we can't forget we have a minus 8 to tag on there. All of this gets divided by h. Now let's go ahead and let's simplify. This is the limit as h goes to 0. We have an 8 plus 4 times 3 is 12, so we have a 12h plus 6h squared plus h cubed minus 8, all divided by h. Now let's look at our terms that cancel. We have an 8 that cancels, so that's great. Notice in the numerator that we have an h common to every term. So I am going to factor out an h, and we'll write this as the limit as h goes to 0. We'll pull out an h, and we have a 12 plus 6h plus h squared, all divided by h. Now you can see that our h's cancel, and we can just go ahead and substitute in that h is going to 0. This gives us 12 plus 0 plus 0, so our limit is equal to 12. Let's now look at our last limit example. This is equal to the absolute value of minus 4 plus 4, all divided by minus 4 plus 4. So this is the absolute value of 0 divided by 0, and we end up with our indeterminate form, 0 divided by 0. Notice in this limit that we have an absolute value function. Whenever you have a limit with an absolute value function, the best thing to do to evaluate it is to break up that absolute value function into pieces. Just as a review, the absolute value of x is equal to positive x when x is greater than or equal to 0, and minus x when x is less than 0. We're going to use this as a model to find out what the absolute value of x plus 4 is equal to. it's just going to be equal to x plus 4 when x plus 4 is greater than or equal to 0, and then minus x plus 4 when x plus 4 is less than 0. Let's now see what this piece is equal to. Let's bring the 4 to the right. So this is just x is greater than or equal to minus 4. And then this piece is x is less than minus 4. I'm going to highlight these because we're going to need that. We're going to break up this limit into our left-hand piece and then our right-hand piece. Let's look at the limit as x approaches minus 4 from the left. That's going to be this piece right here because x is less than minus 4. So we're going to substitute in for our numerator minus the quantity x plus 4. So we have a minus x plus 4 on top. And then down below, we have an x plus 4. These terms cancel. So we're left with a value of minus 1. Now let's look at our right-hand piece. This is the limit as x goes to minus 4 from the right. We're going to plug in x plus 4. So we have an x plus 4 on the top, x plus 4 on the bottom, and we end up with a value of 1. Notice that our limit from the left does not equal our limit from the right. We know from the definition of a limit that it's only going to exist if the limit from the left equals the limit from the right. So we can conclude that the limit as x goes to minus 4 of absolute value x plus 4 all divided by x plus 4 does not exist. So we're going to write this as DNE for our answer. Sometimes when you're evaluating limits, direct substitution or algebraic techniques don't work. When this happens, you can try using the squeeze theorem to evaluate a limit. The squeeze theorem is just a method for finding the limit of a function by squeezing it between two other functions that are easier to evaluate. Let's look at our graph. Suppose we want to evaluate the limit of g of x as x approaches a from both the left and the right. Since g of x lies between f of x and h of x, we can use the squeeze theorem to evaluate its limit. The squeeze theorem tells us that if we have a function g of x and it lies between f of x and h of x, when x is near a and the limit of f of x as x approaches a equals the limit of h of x as x approaches a, and these are both equal to L, then the limit of g of x as x approaches a is also equal to L. Let's look at two examples to see how we can use this squeeze theorem to evaluate limits. In our first example, we are given that f of x lies between 3x and x cubed plus 2 when x is between 0 and 2, and we want to evaluate the limit of f of x as x goes to 1. I think the hardest part of doing these types of limits is to figure out where to start. I always tell students, let's start with what we are given. We are given this expression, 3x is less than or equal to f of x is less than or equal to x cubed plus 2. So that's a good place to start. Now let's look at what we want to find. We want to find the limit as x goes to 1 of f of x. So we'll take the limit as x goes to 1 of all three of these functions. We have the limit as x goes to 1 of 3x less than or equal to the limit x goes to 1 of f of x less than or equal to the limit x goes to 1 of x cubed plus 2. This, in the middle, is what we want to find, so let's evaluate the left-hand limit and the right-hand limit. All we have to do is substitute in that x is going to 1, so on the left we have 3 times 1 less than or equal to the limit x goes to 1 of f of x less than or equal to plugging in 1, we have 1 cubed plus 2. So we see that on the left we have a 3, and on the right we also have a 3. We can use the squeeze theorem then to conclude that the limit as x goes to 1 of f of x is equal to 3. Let's now look at a more complicated example. We're asked to show that the limit of x squared times sine of 1 over x as x approaches 0 is equal to 0. Let's start by evaluating what this limit is. The limit as x approaches 0, x squared sine 1 over x is going to be equal to 0 times sine of 1 divided by 0. We don't know how to evaluate this term. Since we don't know how to evaluate it, I went ahead and I graphed sine of 1 over x so that we can see what's going on as x gets close to 0. You can see that sine of 1 over x has what we call oscillatory behavior. That means that it's oscillating between two values and never settles down to one single value. Because of this, we say that the limit as x goes to 0 of sine 1 over x is what we call does not exist. Let's now combine this with the x squared. We have the limit as x goes to 0, x squared sine 1 over x is equal to the limit x goes to 0 of x squared times the limit x goes to 0 of sine 1 over x. Our first limit is equal to 0, and then our second limit is does not exist. So this leaves us with a big question. What does this combined limit actually equal? Since we can't use algebraic techniques to evaluate it, let's try to use the squeeze theorem. When you look at the graph of sine 1 over x, you can see that it's bounded between this number and this number. The sine of a function theta is always bounded between -1 and 1. We can say then that the sine of 1 over x is also going to be bounded between -1 and 1. And that expression sets us up to being able to use the squeeze theorem. The limit that we want to evaluate is x squared sine 1 over x. So I'm going to take this expression that we just wrote down and multiply each of the three terms by x squared. We get minus x squared less than or equal to x squared sine 1 over x less than or equal to x squared. Now let's apply the limit to all three pieces. We have the limit as x goes to 0 minus x squared less than or equal to the limit x goes to 0 x squared sine 1 over x less than or equal to the limit as x goes to 0 of x squared. This is the limit that we want to evaluate. So what we're going to do is evaluate both of the ends. On the left-hand side, all we have to do is plug in 0, and we get 0, less than or equal to the limit x goes to 0, x squared sine 1 over x. And then on the right, we plug in 0, and we also get 0. Since the left-hand side and the right-hand side are both 0, we can conclude from the squeeze theorem that the limit as x goes to 0, x squared sine 1 over x is equal to 0. Just for fun, I've graphed x squared sine 1 over x so that you can see what this looks like. You can see that the limit of this function is going to go to 0 as x goes to 0. It continues to oscillate all the way down to 0, but the oscillation is bounded by x squared, which goes to 0, so that makes this function have a limit of 0. And that's it. To really get comfortable with evaluating limits, make sure you practice plenty of problems on your own. That's really the only way to learn calculus.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.